There's a kind of silence that follows you through deep space. Not the silence of emptiness, but something heavier. The silence of things that have travelled impossibly far, carrying stories no one was meant to hear. Right now, something is moving through our solar system. You wouldn't notice it without a telescope. Just a faint smudge against the darkness, barely brighter than the stars behind it. But astronomers have been watching it closely, and the more they look, the less sense it makes. It has a tail, like a comet, but comets don't behave this way. It came from somewhere beyond our sun's reach, travelling on a path that will never bring it back. We've only seen 2 others like it, visitors from the space between stars. But this one seems to be made of something different, something that shouldn't be wandering the galaxy alone. On December 19th, it will make its closest approach to our sun. After that, it fades back into the void. The clock is counting down. This is the story of 3I/Atlas, and the possibility that we're watching the last remnant of a star that collapsed long before Earth existed. A fragment that's been drifting in darkness for millions of years, and we just happen to notice it passing through. Let's start with the moment astronomers realised something was wrong. If you're here because you're curious about the universe's deeper mysteries, the kind that don't have easy answers yet, consider subscribing. We'll be following 3I/Atlas through its December passage and breaking down what astronomers discover in real time. Hit the bell so you don't miss what happens next. December 19th, 2025. Mark it on your calendar. Not because something catastrophic will happen, it won't, but because on that day, a visitor from beyond our solar system will pass closer to the sun than it has in millions of years, possibly closer than it's ever been to any star. For astronomers, this is everything. When an interstellar object drifts through our neighbourhood, we get one chance to study it before it disappears forever. And chances like this don't come often. In all of human history, we've only confirmed 3 interstellar visitors. The first one, Oumuamua, was already leaving when we spotted it in 2017. By the time we understood what we were looking at, it was too far away to study properly. The second, Comet 2I/Borisov in 2019, gave us more time, but it behaved exactly like comets we already know. This one is different. 3I/Atlas, officially designated C2024S1 Atlas, was discovered on August 10th, 2024 by the Asteroid Terrestrial Impact Last Alert System in Hawaii. At first glance, nothing seemed unusual. Just another faint object moving against the background stars, flagged by automated detection software. The kind of discovery that happens several times a week. But when astronomers calculated its orbit, something immediately stood out. The trajectory was hyperbolic. That's the technical term for an orbit that doesn't close. A path that comes in from interstellar space, swings around the sun once and heads back out into the galaxy forever. Most objects in our solar system travel on elliptical orbits, bound to the sun by gravity, returning again and again over thousands or millions of years. This object was just passing through. At the time, that alone was enough to generate excitement. Interstellar visitors are spectacularly rare, our solar system is vast, and the space between stars is even more so. For something to cross our path by pure chance means it travelled for hundreds of thousands, maybe millions of years through the void, moving through a galaxy so empty that the nearest star is 4 light-years away. The odds of us noticing it? Vanishingly small. But we did notice. And as autumn progressed and more observations came in, the excitement shifted into something else. Confusion. Here's what made astronomers pause. 3I/Atlas started developing a coma, a faint fuzzy envelope of gas and dust around its nucleus. That's normal for comets. As they approach the sun, solar radiation heats their icy surfaces, causing frozen gases to sublimate and stream away, creating that characteristic hazy glow and sometimes a tail. But the coma around 3I/Atlas looked wrong. Dr. Karen Meach, an astronomer at the University of Hawaii who has spent years studying interstellar objects, noted that the brightness behaviour didn't match standard comet models. The coma was there, yes, but it was asymmetric, faint, and appeared at a distance from the sun where most comets would still be frozen solid. Even stranger spectroscopic analysis, where astronomers split the light from an object into its component wavelengths to identify what chemicals are present, revealed something unexpected. The signatures of carbon-based molecules like C2, decarbon, and CN, cyanogen, were detectable but weak. Much weaker than they should be for a typical comet of this size and distance. It was behaving like a comet, but not quite. Some objects do this. There's a category called Manx comets, rocky bodies that formed in the cold outer regions of a planetary system but lack the typical icy composition. They're rare, but they exist. Maybe 3I/Atlas was something similar formed in another star's Kuiper belt and ejected into interstellar space during some ancient planetary migration. That would have been the easy answer. But as December approaches and 3I/Atlas moves closer to the Sun, the data keeps refusing to fit cleanly into any existing category. Its albedo, the amount of sunlight it reflects, suggests a surface that's darker and possibly more metallic than typical comets. Its density, estimated from how the Sun's gravity tugs on its trajectory, seems higher than expected for an icy body. And then there's the question no one wants to say out loud yet. What if it's not a comet at all, Doctor? Zdeněk Sekanina, a comet specialist at NASA's Jet Propulsion Laboratory, has studied dozens of unusual comets over his career. In a recent correspondence with colleagues, he wrote, "We may be looking at something that formed under conditions entirely unlike anything in our own solar system. The composition suggests processes we don't typically associate with comet formation." So what does that actually mean? It means we don't know. And December 19th is when we'll get our best chance to find out. On that day, 3I/Atlas will reach perihelion, the closest point in its orbit to the Sun. It will pass within approximately 13 million kilometers of our star's surface. That's close. Not dangerous, but close enough that the Sun's intense radiation will heat the object significantly, potentially causing more material to sublimate and stream away. If it's a comet, that moment should tell us. The coma should brighten dramatically. The tail should stretch millions of kilometers behind it. Spectroscopic observations should light up with chemical signatures. If it's something else, well, that's what makes December 19th so important. Space telescopes are already allocated. Hubble has observation windows scheduled. The James Webb Space Telescope, if its crowded schedule allows, may point its infrared eyes toward this visitor. Ground-based observatories across the Northern Hemisphere are preparing campaigns to capture every possible wavelength of light. Because after perihelion, 3I/Atlas will begin fading rapidly. By January it will be too dim for detailed spectroscopy. By February, even the largest telescopes will struggle to track it. Within a year it will be beyond Neptune's orbit, heading back into the darkness between stars. We have 1 month, maybe less. And if astronomers are right about what they're starting to suspect, if 3I/Atlas really is something fundamentally different from the comets and asteroids we know, then this isn't just a close pass by an unusual object. It's a message from a dead star, a fragment that survived something catastrophic, drifted through interstellar space for eons, and happened to pass through our tiny corner of the galaxy at the exact moment in cosmic history when humans were here to notice it. But before we can understand what it's telling us, we need to go back to the beginning. Back to August, when a telescope in Hawaii captured something that shouldn't have been there. August 10th, 2024, Mauna Loa, Hawaii. The Atlas telescope wasn't looking for history that night. It was doing what it always does, scanning the sky in a systematic grid pattern, imaging the same patches of space over and over, looking for anything that moves. Most nights it finds asteroids, objects that belong to our solar system, orbiting the Sun in predictable paths. The software flags them, calculates their orbits, and adds them to a database that's been growing for decades. Routine work. Essential, but routine. But sometimes the software flags something that doesn't fit the pattern. Larry Deneau, a researcher with the Atlas project, was the first to notice the anomaly in the detection pipeline. A new object, faint, around magnitude 19, which means you'd need a decent amateur telescope just to see it as a dim speck. It was moving, but not in the way near-Earth asteroids typically move. The motion was wrong, too fast, and the direction suggested it was coming from outside. Deno ran the preliminary orbit calculation. Then he ran it again. Hyperbolic. That single word changes everything in astronomy. A hyperbolic orbit means the object has more velocity than the sun's gravity can hold on to. It's not captured. It's not going to loop back. It came from somewhere else, and it's leaving. In that moment, sitting at his computer in Hawaii, Deno knew he was looking at only the third confirmed interstellar visitor in human history. But knowing something is interstellar and understanding what it is are two very different things. Over the next few days, observatories around the world turned their attention to this newcomer. The race was on to gather as much data as possible. Position measurements to refine the orbit, photometry to track its brightness, spectroscopy to analyze what it was made of. And that's when the confusion started. Dr. Teddy Coretta, a planetary scientist at Lowell Observatory, was part of the early spectroscopic campaign. His job was straightforward. Point the spectrograph at 3/Atlas, split its reflected sunlight into a rainbow of wavelengths, and see what chemical signatures appeared. What he expected: the clean, strong emission lines of water ice H2O, carbon monoxide CO, or carbon dioxide CO2, sublimating as the object warmed. Standard comet stuff. What he got, something muted. The spectrum showed hints of carbon-based molecules C2 and CN, which do appear in comets, but they were faint, weaker than they should be at that distance from the sun, and other expected signatures were simply missing. It was like looking at a comet through a filter, Coretta later told colleagues. All the right pieces were there, but dimmed, like someone turned down the volume. At first, the explanation seemed obvious. Maybe it was just a small object. Smaller comets have less surface area to sublimate material, so naturally the spectral lines would be weaker. But the brightness data didn't support that theory. Based on how much sunlight 3/Atlas reflected, astronomers estimated its nucleus, the solid core beneath any coma, was somewhere between 500 meters and a kilometer across. Not tiny. Roughly the size of Comet 2I/Borisov, which had produced a spectacular coma visible in amateur telescopes. So why was 3I/Atlas so faint? By September, more observations were rolling in. Photometric monitoring, repeated measurements of brightness over time, showed something strange. The object was getting brighter as it approached the sun, yes, but not in the smooth, predictable way comets usually do. Comets follow what's called the inverse square law with sublimation. As they get closer to the sun, they heat up exponentially, and their brightness increases accordingly. You can predict it with fairly simple physics. 3I/Atlas was brightening but erratically. Some nights it would surge slightly, other nights it would plateau. There was no clear pattern, no easy explanation. Dr. Michael Kelly at the University of Maryland, who specializes in cometary activity, ran the numbers through several models. None of them fit cleanly. Either the nucleus is rotating in a very unusual way, he noted in a preprint paper, or the material sublimating from the surface isn't distributed evenly, or we're not looking at a typical icy comet nucleus. That last possibility, the one nobody wanted to commit to yet, kept nagging at researchers. Then came the albedo measurements. Albedo is simple. It's the percentage of sunlight an object reflects. Fresh snow has a high albedo, around 80 to 90%. It reflects most of the light that hits it. Charcoal has a low albedo, around 4%. It absorbs almost everything. Typical comets have low albedos, around 4 to 6%, because their surfaces are covered in dark, carbon-rich dust. That made sense. Comets are dirty snowballs, after all. But 3I/Atlas, early estimates put its albedo even lower, somewhere around 3 to 4%, darker than most comets, and combined with a weak spectral signatures that suggested something unusual about its surface composition. Maybe it wasn't covered in fluffy dust. Maybe it was rockier, denser. Dr. Jane Liu, who co-discovered the Kuiper Belt and has studied distant solar system objects for decades, reviewed the early data with cautious interest. What we're seeing, she wrote in an email to colleagues, is an object that wants to be a comet. It has a coma, it's outgassing, but it doesn't act like the comets we know. The composition seems off. The activity seemed suppressed. She paused before adding, "We should consider the possibility that it formed in a very different environment than our own solar system's comets." By October, the astronomy community was buzzing with quiet speculation. Not the wild, sensational kind, scientists are cautious by training, but the kind of speculation that happens when data refuses to fit the boxes you've built for it. What kind of environment produces an object like this? A planetary system with different chemistry? A region of space with unusual ice ratios? Or something more extreme, something violent? At the time, no one was ready to say it out loud. But the possibility was starting to form in the back of minds across observatories worldwide. What if 3I/Atlas wasn't a comet at all? What if it was a fragment, a remnant of something that broke apart under forces we don't usually associate with comet formation? The kind of forces that occur when stars die. But before that theory could take shape, astronomers needed to confirm something fundamental. Was 3I/Atlas actually from interstellar space? Or was there any chance, however slim, that it belonged to our solar system and we'd simply miscalculated? The trajectory analysis would settle that question, and the answer would open a door to something far stranger. There's a difference between suspecting something and proving it. When Larry Denneau first saw that hyperbolic trajectory calculation in August, he suspected 3I/Atlas was interstellar, but suspicion isn't enough. In astronomy, extraordinary claims require extraordinary evidence. And claiming an object came from beyond our solar system is about as extraordinary as it gets. So the verification process began. To understand what makes an object definitively interstellar, you need to understand orbital eccentricity. It's a number that describes the shape of an orbit. Perfect circle has an eccentricity of 0. Earth's orbit, which is nearly circular, has an eccentricity of 0.017, barely elliptical. Halley's comet, which travels far beyond Neptune before swinging back toward the Sun, has an eccentricity of 0.967, a highly stretched ellipse but still bound to the Sun. Anything with an eccentricity greater than 1 is hyperbolic. It's not orbiting, it's escaping. The first calculations put 3I/Atlas at an eccentricity around 1.00003. That's hyperbolic, yes, but barely. And here's the problem. Measurement errors exist. When you're tracking a faint object millions of kilometers away, calculating its precise position and velocity involves uncertainty. Small errors in measurement can shift an eccentricity calculation from 0.9998 to 1.0002. So was 3I/Atlas truly interstellar, or was it a long-period comet from the Oort cloud that we'd simply mismeasured? The answer required more data, lots of it. Over the course of September and October, observatories worldwide contributed position measurements. Every night it was visible, someone was watching. The Minor Planets Center, the official organization that tracks small solar system bodies, collected observations from over 40 different telescopes across 6 continents. Each observation refined the orbit slightly. Each calculation narrowed the uncertainty. By mid-October, the eccentricity estimate had stabilized. 1.00027, with an uncertainty margin small enough to rule out any bound orbit. 3I/Atlas was confirmed, definitely unambiguously interstellar. But eccentricity alone doesn't tell you where something came from. For that, you need to calculate the incoming velocity vector, essentially rewind the object's motion backward in time, and see what direction it was travelling before the sun's gravity bent its path. Dr. David Farnokia at NASA's Jet Propulsion Laboratory specialises in exactly this kind of work. His team uses sophisticated software to model how objects move through the solar system, accounting for gravitational influences from all the planets, pressure from solar radiation, even the tiny push from outgassing if the object is active. When they ran the trajectory backward for 3I/Atlas, something interesting emerged. The object wasn't coming from the direction of any particular star. That's actually normal. Space is so vast, and interstellar travel takes so long, that even if 3I/Atlas was ejected from a specific stellar system, that system has since moved. Stars orbit the galactic center just like planets orbit stars. Over hundreds of thousands of years, everything shifts position. What mattered was the velocity. Before entering our solar system, 3I/Atlas was travelling at approximately 29 kilometers per second relative to the local standard of rest, the average motion of stars in our galactic neighbourhood. That's fast, but not unusually so. It's within the range you'd expect for an object drifting through interstellar space, not gravitationally bound to any star. For comparison, Voyager 1, humanity's fastest and most distant spacecraft, is travelling at about 17 kilometers per second. 3I/Atlas was moving considerably faster, and it had been doing so for a very, very long time. So how long? That's harder to pin down. Without knowing exactly where it came from, you can only estimate. If 3I/Atlas originated from a star system 50 light-years away and has been travelling at 29 kilometers per s, the math works out to roughly 500,000 years in transit. 500,000 years, drifting through the cold, empty space between stars. On Earth, 500,000 years ago, modern humans were just beginning to spread across Africa. We hadn't invented agriculture, we hadn't built cities, we were still figuring out how to control fire reliably. And this object was already travelling through the void, silent and frozen, carrying whatever secrets were embedded in its composition. Now here's what makes 3I/Atlas particularly significant. It's only the third confirmed interstellar object we've ever detected, but it might be the most scientifically valuable. The first, Oumuamua, was revolutionary. It proved interstellar objects pass through our solar system at all. Before 2017, that was theoretical. After Oumuamua, it was fact. But we discovered it too late. It was already outbound, racing away from the sun faster than any of our telescopes could keep up. We got a few blurry images, some basic measurements, and then it was gone. The second 2I/Borisov was better. We caught it earlier in its approach, which gave us months to study it, and what we learned was comforting, actually. It looked like a comet. It acted like a comet. Spectroscopy showed water, carbon monoxide, all the usual comet chemistry. It suggested that comet formation might be a universal process, that solar systems across the galaxy produce similar objects. That was reassuring. The universe seemed a bit more understandable. But 3I/Atlas? It's refusing to be reassuring. It has some comet-like features, yes. But the more data astronomers collect, the more it looks like something we haven't encountered before. The composition seems off. The activity seems suppressed. And the albedo measurements, that unusually low reflectivity, keep suggesting a surface that's rockier, denser, maybe even metallic. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury, who has studied both interstellar visitors, put it bluntly in a recent interview. With Borisov, we saw what we expected to see. With 3I/Atlas, we're seeing something new. And new in astronomy usually means we're about to learn something important. The statistical reality makes this even more striking. Interstellar objects are rare, not because they don't exist, but because space is incomprehensibly large and these objects are incredibly small. Detecting one requires it to pass through a tiny region of space where our telescopes happen to be looking at exactly the right time. We've now found 3, and 2 out of 3 seem normal. 1 does not. That ratio bothers astronomers. If 3I/Atlas represents a common type of interstellar object, if fragmented, dense, metal-rich bodies are drifting through the galaxy in large numbers, then we've been fundamentally underestimating the diversity of material travelling between stars. And that raises an uncomfortable question. What kind of event produces objects like this? What violent energetic process tears matter apart, scatters it into interstellar space and sends it wandering for hundreds of thousands of years? The answer might be written in the faint light reflecting off 3I/Atlas right now, in the weak spectral lines, in the unusual coma behaviour, in the possibility that we're not looking at something that formed gently in a protoplanetary disk, but something that survived an ending. If you've ever seen a comet in the night sky, really seen one, not just a photograph, you know they're beautiful. That soft, glowing haze around the nucleus, the delicate tail stretching away from the sun, sometimes spanning millions of kilometres. That glow is the coma, and it's one of the most fundamental features of what makes a comet a comet. The physics are straightforward. A comet's nucleus is mostly ice, water ice, carbon dioxide ice, frozen methane and ammonia, mixed with rock and dust. As the comet approaches the sun, solar radiation heats the surface. The ices don't melt, they sublimate, going directly from solid to gas. That gas carries dust particles with it, creating a cloud that surrounds the nucleus and reflects sunlight. The closer to the sun, the more active the sublimation, the brighter the coma. It's predictable, reliable. We've been observing comets for thousands of years, and their behaviour follows patterns we understand. 3I/Atlas has a coma. That much is clear from the images, but it's the wrong coma. Dr. Matthew Knight, a comet specialist at the US Naval Academy, was among the first to notice the discrepancy. In late September, he obtained deep imaging of 3I/Atlas using a 4-metre telescope in Arizona. The exposure times were long, several minutes per frame, designed to capture as much faint light as possible. When he processed the images, the coma was visible, barely, a faint fuzzy envelope around the central point of light. It looked anemic, Knight later said in a presentation to colleagues, like a comet that was trying to be active but couldn't quite manage it. The problem wasn't just brightness, it was structure. Most comet comas are roughly symmetric, a circular or slightly oval cloud centered on the nucleus. As material sublimates, it expands outward in all directions, driven by the pressure of escaping gas. You get some asymmetry from the comet's rotation, and sometimes jets erupt from specific areas on the surface, but the overall shape is predictable. 3I/Atlas's coma was lopsided. One side appeared slightly brighter than the other, and the edge was poorly defined, fading gradually into the background rather than having a distinct boundary. That suggested uneven outgassing. Material was escaping from some parts of the surface but not others. That can happen if a comet's nucleus is heterogeneous, if some areas are icier and others are more rocky, but usually you see clear jet structures, distinct plumes of material shooting out from active regions. Here there were no obvious jets, just a weak asymmetric haze. Then came the spectroscopy results, and things got stranger. Dr. Cyrielle Opitom at the University of Edinburgh led a spectroscopic campaign using the Very Large Telescope in Chile. Her goal was to identify exactly what molecules were present in the coma, the chemical fingerprints that would tell us what 3I/Atlas was made of. Standard comet spectra show strong emission lines. When sunlight hits molecules like water, H2O, cyanogen, Cn, or dicarbon, C2, those molecules absorb specific wavelengths of light and re-emit them. The result is bright, distinctive lines in the spectrum that essentially label what's there. Opitom's spectra showed Cn and C2. Both are carbon-based molecules commonly found in comets, but they were faint, unexpectedly faint. At the distance 3I/Atlas was from the Sun, about 1.5 astronomical units in early October, we should have been seeing much stronger emission, Opitom noted in her preliminary analysis. The production rates we calculated were roughly 10 times lower than what we'd expect for a typical comet of this size. Production rate is the technical term for how much gas a comet releases per second. It's measured in molecules per second, and for comets at this distance, you typically see numbers in the range of 1026 to 1027 molecules per second for water, and proportionally less for other species. 3I/Atlas was producing around 1025 molecules per second of Cn. That's not zero, it's definitely active, but it's weak, like the comet was outgassing reluctantly. And here's the critical part, the ratio was off. In typical comets, the relative abundances of different molecules follow predictable patterns. The ratio of Cn to C2, for example, usually falls within a known range. It's not exact, comets vary, but there's a baseline. 3I/Atlas's ratio was skewed. There was more C2 relative to Cn than expected, not wildly so, but enough to make spectroscopists pause. It suggests either an unusual parent molecule composition, Opitom explained, or that the sublimation process is being inhibited somehow. Perhaps the surface has a layer of refractory material, rocky, non-volatile stuff, that's insulating the ice underneath. That would explain the weak activity. If the surface is covered in a thick crust of dust or rock, only small patches of ice would be exposed. Sublimation would be limited to those exposed areas, resulting in a faint coma despite potentially having ice in the interior. But if that's true, it raises another question. Why is the crust so thick? Most comets develop some surface crusting over time. Every time they pass close to the Sun, the ices near the surface sublimate away, leaving behind a lag deposit of dust and rocky particles. But that process takes multiple passes. Comets from the Oort cloud, on their first trip into the inner solar system, usually don't have thick crusts yet. Their surfaces are fresh. 3I/Atlas is on its first and only pass through our solar system. It's never been this close to a star before, at least not in the time it's been drifting through interstellar space. So where did the crust come from, Doctor? Bin Yang at the European Southern Observatory, who reviewed the early spectroscopic data, offered a possibility. If this object formed in an environment that was already warm, or if it experienced heating events in the past, the surface could have been processed before it ever left its home system. We might be looking at an object that was thermally altered long ago. Thermally altered, heated, processed. Those are careful scientific words, but they point towards something violent. Not the gentle, gradual heating of a comet in a stable orbit. Something more extreme. Something that would bake the surface, drive off the volatile ices, and leave behind a dense, rocky crust. The kind of heating that occurs during stellar events. When astronomers started pulling on that thread, started asking what scenarios could produce an object with these specific characteristics, they kept arriving at the same uncomfortable conclusion. 3I/Atlas might not have formed in a protoplanetary disk at all. It might be a fragment, piece of something larger that broke apart under intense heat and pressure. A remnant. And if that's true, then the question isn't what kind of comet is this? The question is, what did this used to be part of? There are things in the universe that don't survive. Planets get swallowed by their dying stars. Moons are torn apart by tidal forces. Asteroids shatter in collisions. But these are relatively gentle processes, astronomically speaking. The pieces left behind still resemble what they once were. Then there are stellar collapses, and nothing survives those intact. When a star runs out of fuel, what happens next depends on its mass. Our Sun, for example, will eventually swell into a red giant, shed its outer layers, and leave behind a white dwarf. A dense, Earth-sized ember that will slowly cool over billions of years. But more massive stars, they die violently. If a star is heavy enough, its core collapses catastrophically, triggering a supernova explosion that briefly outshines entire galaxies. The shockwave rips through everything, planets, asteroids, comets, obliterating them or scattering their fragments into interstellar space at tremendous velocities. That's one way to create interstellar debris, but it's not the only way. There's another category of stellar death that's less dramatic but equally destructive. The asymptotic giant branch phase. Stars between 1 and 8 times the Sun's mass go through this stage near the end of their lives. They expand enormously, pulsate irregularly, and shed mass in violent stellar winds. Their outer layers blow away, sometimes engulfing and destroying any planets in close orbits. What remains is the core, a white dwarf. And here's what matters for our story. White dwarfs aren't made of hydrogen or helium like normal stars. They're composed of heavier elements, carbon, oxygen, sometimes even heavier metals depending on the star's original mass. They're incredibly dense. A teaspoon of white dwarf material would weigh several tons on Earth. They're also not perfectly stable. Some white dwarfs have companion stars. If the companion gets close enough, the white dwarf's gravity can pull material off it. A process called accretion. That stolen material piles up on the white dwarf's surface, compressing and heating until it ignites in a thermonuclear explosion called a nova. In extreme cases, if enough material accumulates, the entire white dwarf can explode in a Type Ia supernova, leaving nothing behind. But there's a middle ground. A scenario that doesn't completely destroy the white dwarf, but fragments it. Dr. Philip Podsiadlowski, an astrophysicist at Oxford who specialises in stellar evolution, has modelled these kinds of events. In some binary systems, the interaction between a white dwarf and its companion can become unstable. Tidal forces stretch and stress the white dwarf. If it's rotating rapidly, or if the companion's orbit decays quickly, the white dwarf can be partially disrupted. Not vaporized. Disrupted. Pieces break off. Fragments composed of incredibly dense, carbon-rich, oxygen-rich, possibly iron-rich material. These fragments don't have the gravitational strength to pull themselves back together. They're too small, and they're moving too fast. Flung outward by the violence of the disruption, they become interstellar wanderers, and they would look very different from normal comets. So what would a white dwarf fragment actually look like if it passed through our solar system? First, it would be dense. Much denser than a typical comet, which is mostly ice and loosely packed dust. A white dwarf fragment would have a density closer to rock or metal, several grams per cubic centimetre, instead of less than 1. That matches what we're seeing with 3I/Atlas. The trajectory perturbations, the tiny ways the sun's gravity affects its path, suggest a higher density than typical comets. Second, it would have a low albedo. White dwarf material, especially carbon-rich compounds, would appear dark. Carbon in its graphite form is black. Even if the surface has been weathered by cosmic rays during millions of years in interstellar space, it would remain dark. 3I/Atlas has an estimated albedo around 3 to 4%, darker than most comets. Third, it would show weak cometary activity. If the fragment retained any volatile materials, perhaps from material accreted during its journey through interstellar space, or from the outer layers of the disrupted white dwarf, those volatiles would be buried beneath a refractory crust. Heating from the sun might sublimate small amounts, creating a faint coma, but nothing like the vigorous outgassing of a typical comet. That's exactly what we're observing. A faint asymmetric coma with weak spectral signatures. Fourth, the composition would be unusual. Instead of water ice and simple organic molecules, you'd expect carbon-based compounds, possibly with traces of heavier elements. The spectroscopic ratios would be off compared to normal comets. Again, that fits. Dr. Daryl Seligman, a postdoctoral researcher at Cornell who has studied unusual solar system objects, reviewed the 3I/Atlas data in November and wrote a provocative preprint paper. His title was careful, on the possibility of compact object fragments as interstellar visitors. In it, he didn't claim 3I/Atlas was definitely a white dwarf fragment. Science doesn't work that way. Instead, he laid out the evidence and showed that the white dwarf fragment hypothesis explained the observations better than the comet hypothesis. We're not saying comets can't look like this, Seligman noted in the paper's discussion section. We're saying that if you want to build an object with these specific properties, high density, low albedo, weak activity, unusual composition, starting with white dwarf material gives you a more straightforward path than starting with comet material. Of course, extraordinary claims require extraordinary evidence, and right now, the evidence is suggestive, not conclusive. The biggest challenge is the spectroscopy. We have limited data on what a white dwarf fragment spectrum would actually look like. We've never observed one before, assuming they even exist. The molecules we're detecting, CN, C2, are carbon-based, which is consistent with the hypothesis, but they're also found in regular comets. What we really need is a detection of something definitively unusual. A spectral line from an exotic compound that wouldn't form in a normal protoplanetary disk, or a significantly higher abundance of heavy elements like iron or nickel. Those observations might be possible as 3I/Atlas approaches perihelion. The increased solar heating could drive off more material, brightening the coma and making spectroscopy easier. But there's a risk. If 3I/Atlas is a fragment of a disrupted white dwarf, the intense heating at perihelion might not produce more activity, it might produce less. The object might simply absorb the heat without sublimating much material at all. And if that happens, if 3I/Atlas passes through perihelion without brightening significantly, it would be another piece of evidence supporting the fragment hypothesis. because comets don't stay quiet when they're that close to the sun. Rocks do. So here we are, watching an object that might be the first confirmed fragment of a dead star ever detected. A piece of something that was destroyed in a stellar catastrophe hundreds of thousands, maybe millions of years ago. A remnant that's been drifting through the galaxy ever since, carrying the chemical signature of a white dwarf's interior in its composition. If that's what 3I/Atlas really is, then it raises a profound question: where did it come from? Not just which star system, but which star? And is it still out there? Or has it vanished completely? Evidence in astronomy is rarely dramatic. It doesn't arrive in neat packages with clear answers. Instead, it accumulates slowly, pixel by pixel, spectrum by spectrum, until a picture begins to form. Sometimes that picture confirms what you expected, and sometimes it shows you something you didn't know was possible. For 3I/Atlas, the evidence has been accumulating since August. Each observation adds another piece to the puzzle, and while no single piece proves the white dwarf fragment hypothesis, together they form a pattern that's hard to ignore. Let's start with the density. Calculating the density of a distant object is tricky. You need two things, mass and volume. Volume you can estimate from brightness, if you know the albedo. Mass is harder. You can't put a comet on a scale. Instead, you measure how the sun's gravity affects its trajectory. Even tiny deviations from a perfect hyperbolic orbit can reveal information about the object's mass. For 3I/Atlas, the orbital data collected through October allowed astronomers to place constraints on its density. The exact number depends on assumptions about its shape and rotation, but the estimates cluster around 3 grams per cubic centimetre. That's significant. Typical comets have densities well under 1 gram per cubic centimetre. Comet 67P/Churyumov-Gerasimenko, which the Rosetta spacecraft studied up close for 2 years, has a density of just 0.53. It's fluffy, more like a pile of snow than solid rock. Asteroid densities are higher, usually 4 grams per cubic centimetre, depending on composition. But 3I/Atlas isn't following an asteroidal trajectory. It has a coma. It's active. So we have an object that's dense like an asteroid, but active like a comet. That's unusual. Not impossible. There are some high-density comets known in our solar system, but unusual enough to warrant attention. White dwarf material, much denser. But a fragment wouldn't be pure white dwarf core material. It would be a mix, some dense carbon and oxygen from the interior, possibly mixed with lighter elements from the disrupted star's outer layers or material accreted during interstellar travel. A density of 2 to 3 G per cubic centimetre fits that scenario. Next, the albedo measurements. Dr. Rosita Kokotanikova at the European Space Agency has been leading an effort to refine the albedo estimate using photometry from multiple observatories. The challenge is separating the brightness of the nucleus from the brightness of the coma. Even a faint coma contributes scattered light, and you need to subtract that carefully to see the nucleus itself. By late November, her team had narrowed the albedo to approximately 0.03. That's 3%, meaning the surface reflects only 3% of the sunlight that hits it and absorbs the rest. That's darker than most comets we've measured, Kokotanikova noted in a conference presentation. And it's darker than most carbonaceous asteroids. We're looking at a surface that's exceptionally good at absorbing light. Carbon in its graphite form has an albedo around 0.05-0.10. Weathered carbon compounds, exposed to cosmic rays for hundreds of thousands of years, could go lower. So could surface materials rich in iron oxides or complex organic polymers. The point is, darkness doesn't prove anything by itself, but it's consistent with a fragment hypothesis. It's what you'd expect from a thermally processed, carbon-rich surface that's been wandering through space for eons. Then there's the spectroscopy, which is where things get genuinely interesting. In early November, Michael Kelly's team at the University of Maryland obtained high-resolution spectra using the Keck Observatory in Hawaii. They were looking specifically for oxygen emission lines, a signature that would indicate water ice sublimation. In typical comets, oxygen emission is strong. Water, H2O, is the dominant volatile, and when it breaks apart in sunlight, it produces atomic oxygen that emits characteristic wavelengths. In 3I/Atlas, the oxygen lines were there but weak, very weak. The oxygen to carbon ratio was inverted compared to normal comets, Kelly explained in a follow-up paper. We're seeing more carbon emission relative to oxygen than we'd expect if water ice was the primary volatile driving the activity. That could mean several things. Maybe the surface ice is depleted in water and enriched in carbon monoxide or carbon dioxide. Maybe the ice is buried so deep that only carbon-rich molecules are escaping. Or maybe, and this is the intriguing possibility, the object simply doesn't have much water to begin with. White dwarf fragments wouldn't necessarily contain water. The temperatures and pressures during a white dwarf disruption would drive off most volatiles. What remains would be refractory compounds, materials that can withstand high heat. But then, where is the coma coming from? One explanation: surface ice is accreted during interstellar travel. When an object drifts through the interstellar medium for hundreds of thousands of years, it sweeps up trace amounts of gas and dust. That material can freeze onto the surface. It wouldn't be a thick layer, maybe just meters deep at most, but it would be enough to create a faint coma when heated. And because interstellar ices have different compositions than solar system ices, more carbon monoxide, more simple organics, less water, the spectroscopic signature would look off. Doctor. Konstantinos Karambalasas at the University of Athens has been modelling this scenario. His simulations show that an object with a refractory core and a thin mantle of accreted interstellar ice would produce exactly the kind of weak carbon-rich coma we're observing. It's not a comet with ice throughout, he explained. It's a rock with a frosting of ice on the outside, and as that frosting sublimates away, what's left is the dense dark core underneath. That model predicts something testable. The activity should fade faster than a typical comet as it approaches perihelion. A thin ice layer would sublimate completely fairly quickly, leaving only the inert core behind. If 3I/Atlas brightens dramatically at perihelion and stays bright, that would challenge the fragment hypothesis. It would suggest there's more ice than expected. But if it brightens modestly and then fades quickly, or worse, if it doesn't brighten much at all, that would be strong evidence that we're not looking at a typical icy comet. There's one more piece of evidence worth mentioning, though it's more subtle: the rotation. Most comets rotate irregularly. As jets of gas erupt from their surfaces, the escaping material creates torque, changing the spin rate and axis unpredictably. It's like a chaotic sprinkler spinning in random directions. 3I/Atlas appears to be rotating smoothly. Photometric observations show periodic brightness variations, suggesting a rotating nucleus with an uneven shape or surface, but the period seems stable, around 8-9 hours per rotation, with no obvious signs of the kind of erratic behaviour you'd expect from active jetting. That's consistent with minimal outgassing. If only a small fraction of the surface is active, the torque effects would be weak and the rotation would stay steady. It's a small detail, but in astronomy, small details accumulate, and right now they're all pointing in the same direction, towards something that isn't quite a comet, something denser, darker, and older than the icy bodies we're used to seeing, something that might have witnessed the death of a star. Every object carries its history and its motion. The path 3I/Atlas is following through our solar system isn't random. It's a trajectory shaped by gravity, velocity, and time. And if you have enough data, precise enough measurements of position and speed, you can run the physics backward. You can trace where it came from. This is one of astronomy's most elegant detective techniques. Given an object's current position, velocity, and direction, you can rewind its journey through space like playing a film in reverse. The sun's gravity bends the path inward as the object approaches, so you correct for that. The planets tug on it slightly as it passes, so you account for those perturbations too. Eventually you arrive at a velocity vector, the direction and speed the object had before entering our solar system. For 3I/Atlas, that calculation places its origin somewhere in the general direction of the constellation Lyra. Not from any specific star we can identify, Space is too vast and stars have moved too much, but from that general region of the sky, the velocity tells us more, approximately 29 kilometers per second relative to the local standard of rest. That number is important because it constrains how far the object could have travelled. At 29 kilometers per s, covering 1 light year takes about 10,000 years. 10 light years? 100,000 years? 50 light years? 500,000 years. Stars within 50 light years of our Sun are relatively well catalogued. We know most of them. We know their types, their ages, their characteristics. So if 3I/Atlas is a fragment from a stellar disruption, and if it's been travelling for around 500,000 years, then the source star should be somewhere within that bubble. But here's the challenge. Stars move. Our Sun orbits the Milky Way's centre at about 220 kilometers per second, completing one orbit every 225 million years. Other stars in our neighbourhood have similar velocities, but not identical. Some are moving faster, some slower, some in slightly different directions. Over 500,000 years, those differences add up. A star that's 50 light years away now might have been 52 light years away when 3I/Atlas began its journey. Or 48. The uncertainty compounds. Dr. Corinne Baylor-Jones at the Max Planck Institute for Astronomy specialises in exactly this kind of stellar archaeology. His team maintains detailed models of stellar positions and velocities in our galactic neighbourhood, using data from the Gaia spacecraft, a European satellite that has measured the positions and motions of over 1 billion stars with unprecedented precision. When 3I/Atlas was confirmed as interstellar, Baylor-Jones ran a reverse trajectory analysis. He rewound the object's motion backward through time and simultaneously rewound the motions of nearby stars. The goal? Find close encounters, moments in the past when 3I/Atlas would have passed near a star. The results were inconclusive. We identified about a dozen candidate stars that 3I/Atlas might have passed within a few light years of during the past million years, Baylor-Jones explained in a preprint, but the uncertainties are large. We can't pinpoint a single source with confidence. Part of the problem is measurement precision. We know 3I/Atlas's current velocity to within a few meters per second, which is impressive. But over hundreds of thousands of years, even tiny uncertainties multiply. A velocity error of just 10 meters per second translates to an uncertainty of hundreds of light years over 1 million years. The other problem is that we don't know exactly when 3I/Atlas left its source. If it's been travelling for 300,000 years, the search radius is different than if it's been travelling for 700,000 years. Still, the candidate list is intriguing. Among the possibilities, several G-type stars similar to our Sun, a couple of K-type stars slightly cooler and smaller, and one M-type red dwarf. All of them are old enough to have potentially gone through late-stage evolution if they were more massive in the past. But none of them show obvious signs of recent disruption. No debris disks, no unusual brightness variations, no companion white dwarfs that we can detect. That doesn't rule them out. A stellar disruption that happened 500,000 years ago wouldn't necessarily leave visible evidence today. Any debris that wasn't flung into interstellar space would have long since fallen back into the remnant white dwarf or dissipated. The system would look quiet again. There's another possibility, though. One that's less satisfying but perhaps more likely. The source star might not be in our immediate neighbourhood anymore. If 3I/Atlas was ejected during a stellar disruption with a velocity significantly higher than 29 kilometers, say 50 or 60 kilometers, and then was slowed by interactions with the interstellar medium over time, it could have originated from much further away. 100 light years, maybe more. At those distances, the number of candidate stars increases dramatically, and the chances of identifying the specific source drop to nearly zero. So we're left with uncertainty. We know 3I/Atlas came from somewhere out there, but we can't point to a specific star and say that one. What we can do is think about the journey itself. 500,000 years, probably longer, drifting through the space between stars. The interstellar medium isn't truly empty. There's gas, mostly hydrogen, about 1 atom per cubic centimetre on average. There's dust. There's radiation from distant stars. But it's so sparse that an object the size of 3I/Atlas would barely notice it. The drag would be negligible. The collisions with dust grains would be rare. It would be a profoundly quiet journey. No sunlight warming the surface. No planetary companions in orbit. No cometary activity. Just a cold, dark fragment tumbling slowly through the void, its surface temperature hovering just a few degrees above absolute zero. Cosmic rays would bombard it, high-energy particles from supernovae and other violent events across the galaxy. Over hundreds of thousands of years, those impacts would gradually alter the surface chemistry, darkening it, creating complex organic compounds from simpler molecules. That's called space weathering, and it's part of why 3I/Atlas looks so dark now. Occasionally, maybe once every few thousand years, it would sweep through a slightly denser region of the interstellar medium. A tendril of gas from an old supernova remnant or the edge of a molecular cloud, trace amounts of material would freeze onto the surface. Water molecules, carbon monoxide, simple organics. Not much. Maybe just a few meters worth over the entire journey, but enough to create the thin mantle of ice that's sublimating now. For nearly all of that journey, 3I/Atlas was invisible, too far from any star to reflect light, too cold to emit infrared radiation. It might as well not have existed. And then, purely by chance, it drifted into our solar system. The sun's gravity bent its path inward. Solar radiation began warming the surface. The thin ice mantle started sublimating, creating the faint coma that Atlas Hawaii detected on that August night. After 500,000 years of silence, 3I/Atlas became visible for a few months, and then, assuming we're right about what it is, it will fade back into darkness, carrying the secret of its origin with it, unless we can learn everything we need to know before it disappears. That's why December 19th matters. Science progresses through anomalies. For decades, astronomy operated under comfortable assumptions. Comets came from the Oort cloud or the Kuiper belt. Asteroids formed in the early solar system and stayed there. The space between stars was mostly empty except for gas and dust. Then Oumuamua arrived in 2017, and suddenly we had to accept that interstellar objects pass through our solar system. That was a conceptual leap, but not a paradigm shift. The universe was larger and more connected than we'd appreciated, but the basic rules still held. If 3I/Atlas is what some astronomers think it might be, a fragment of a disrupted white dwarf, the implications go deeper. Let's start with the most immediate question. How common are these fragments? We've now detected 3 interstellar objects. 2 appear to be relatively normal. Oumuamua, which might be a comet or asteroid, and 2I/Borisov, which is definitely a comet. 1, 3I/Atlas, looks anomalous. That's a ratio of 1 in 3. If that ratio holds across the broader population of interstellar objects, it suggests something profound. Stellar disruption fragments might be as common in the galaxy as comets and asteroids. Think about what that means. Every white dwarf disruption, and these events, while not frequent, happen regularly on galactic timescales, could scatter hundreds or thousands of fragments into interstellar space. Those fragments wander for millions of years, crossing vast distances, occasionally passing through other star systems. Our galaxy is filled with them. We just haven't been able to see them until now. Dr. Avi Loeb at Harvard, who has studied interstellar objects extensively, puts it this way. If 3I/Atlas confirms the fragment hypothesis, we'll need to rethink our estimates of the interstellar object population. We've been assuming most interstellar visitors are comets or asteroids, but there could be an entirely separate population of stellar remnants that we haven't accounted for. That has implications for stellar evolution theory. White dwarf disruptions aren't supposed to be common. Most white dwarfs cool quietly over billions of years without incident. But if fragments like 3I/Atlas are relatively abundant, it suggests disruptions happen more often than models predict. Maybe binary interactions are more violent than we've assumed. Maybe tidal forces in certain configurations are strong enough to tear white dwarfs apart without triggering a full supernova. Maybe there are disruption mechanisms we simply haven't considered. The existence of these fragments would be a clue, a data point that theorists would need to incorporate into their models of how stars die. Then there's the question of composition. If we could analyze 3I/80 up close, land a spacecraft on it, drill into the surface, examine the interior, we'd be looking at material from a white dwarf's core. That's something we've never been able to study directly. White dwarfs are laboratories for extreme physics. The pressures and densities in their interiors are so intense that matter behaves in ways we can barely replicate on Earth. Carbon crystallizes into structures we can only approximate in simulations. Oxygen exists in exotic high-pressure phases. A fragment would give us a sample, not pristine, it's been weathered by millions of years in space, but still valuable. It would tell us about nuclear processes that occurred in that star's final stages. It would constrain our understanding of stellar nuclear synthesis. It would be like having a meteorite from inside a star. Of course, we're not landing a spacecraft on 3I/Atlas. We barely had time to detect it, let alone launch a mission. But if these objects are as common as the current ratio suggests, we'll encounter more of them, and eventually we might be able to plan for it. Build spacecraft that can launch on short notice when an interstellar fragment is detected. Intercept it, study it up close, maybe even return samples to Earth. That's decades away at minimum, but 3I/Atlas is showing us it's possible. There's another implication, less scientific but equally interesting. The question of what happens to planetary systems during these disruptions. If 3I/Atlas came from a white dwarf disruption, that white dwarf was once a normal star, and normal stars have planets. What happened to them? In most cases, they don't survive. When a star swells into a red giant during its late stages, it engulfs the inner planets. They're vaporized, consumed by the expanding stellar envelope. Outer planets might survive, but their orbits are altered by the mass loss as the star sheds its outer layers. Then, if the white dwarf undergoes a violent disruption, any remaining planets are either destroyed in the event or flung into interstellar space by the sudden gravitational changes. It's a bleak picture. Entire planetary systems wiped out. But here's the thing. We don't know if those systems had life. We don't know if any planets in the habitable zone had developed biospheres before their star died. We probably never will. 3I/Atlas might be the only remnant of that system. A fragment carrying in its composition the chemical signature of a star that once shone steadily for billions of years. A star that might have had planets, that might have had, though the odds are infinitesimally small, something living on one of those planets. That's pure speculation, of course. But it's the kind of speculation that reminds you what we're actually looking at when we study objects like this. Not just rocks, not just data points, echoes. The final implication is perhaps the most humbling, the realization of how little we see. 3I/Atlas was only detected because it developed a faint coma as it approached the sun. That activity made it just bright enough for our telescopes to spot. If it had been a purely inert fragment, no accreted ice, no outgassing, it would have passed through our solar system completely unnoticed. How many have already done exactly that? How many stellar fragments, asteroid-sized chunks of white dwarf material, have drifted through the space between Earth and Mars without anyone knowing? The answer is, we have no idea. But it's probably more than we'd like to think. The galaxy is full of invisible traffic. Most of it never comes close to us. The stuff that does pass nearby is usually too small or too dark to detect unless it does something unusual, like develop a coma or reflect sunlight at just the right angle. We're looking at the universe through a keyhole, and occasionally something interesting walks past. 3I/Atlas walked past, and we happened to be watching. Now the question is whether we can learn enough before it walks away. December 19th is approaching, telescopes are ready, observers are scheduled. Whatever happens at perihelion, it will tell us something. Either 3I/Atlas will brighten dramatically, behaving more like a comet than we expected, forcing us to reconsider the fragment hypothesis. Or it won't, and we'll have to accept what the data has been suggesting all along. that we're watching the remnant of a star that died before humans existed, passing through our small corner of space on a journey that will never end. There's a particular kind of urgency that happens in astronomy when something rare is passing through, and you won't get another chance. It's not panic, it's not desperation, it's a focus, coordinated intensity. Telescope time gets reallocated. Observing proposals are fast-tracked. International collaborations form overnight. For 3I/Atlas, that urgency kicked in the moment astronomers realised what they might be looking at. By late November, observation campaigns were already in motion across the Northern Hemisphere. Ground-based telescopes from Hawaii to the Canary Islands had carved out dedicated time blocks. Space telescopes, with their perpetually oversubscribed schedules, were being petitioned for precious observation windows. The goal was clear: capture as much data as possible before, during and after perihelion on December 19th. Dr. Matthew Knight at the US Naval Academy is coordinating one of the major ground-based campaigns. His team has secured time on several large telescopes, including the 4.3-metre Discovery Channel telescope in Arizona and the 3.6-metre Canada-France-Hawaii telescope on Mauna Kea. We're focusing on multi-wavelength photometry and high-resolution spectroscopy, Knight explained in a recent coordination meeting. We need to track how the brightness changes as it approaches the Sun, and we need detailed spectra to identify every molecule we can in the coma. The photometry, repeated brightness measurements, will reveal whether 3I/Atlas follows the expected brightening curve for a comet or deviates from it. If it's a fragment with only a thin mantle of accreted ice, the activity should peak and then drop off quickly as the ice sublimates away. The spectroscopy is where the real answers might come. Every molecule in the coma has a unique spectral signature. Water produces certain emission lines. Carbon monoxide produces others. If something unexpected shows up, maybe a hint of heavier elements like iron or nickel sublimating from the surface, that would be strong evidence for the fragment hypothesis. But spectroscopy is difficult. 3I/Atlas is faint, and splitting its light into a spectrum makes it even fainter. You need large telescopes, long exposure times, and clear skies. And you need luck. Dr. Cyril Opitham's team at the University of Edinburgh has been allocated time on the Very Large Telescope in Chile, one of the most powerful ground-based observatories in the world. They're planning observations around perihelion using VLT's high-resolution spectrograph. We're hoping to detect emission lines from CN, C2, and if we're lucky, some oxygen, Opitham said. But we're also looking for anything unusual, any spectral feature that doesn't match standard comet models. The challenge is timing. 3I/Atlas will be closest to the Sun on December 19th, but that doesn't mean it will be easiest to observe on that exact date. The Sun's position in the sky matters. If 3I/Atlas is too close to the Sun from Earth's perspective, observing it becomes impossible. The sky is too bright, and the object is too close to the horizon. Observing windows are narrow. A few hours after sunset, or a few hours before sunrise, when the sky is dark enough but 3I/Atlas is still above the horizon. Professional astronomers aren't the only ones watching. Amateur astronomers have played a surprisingly important role in tracking 3We/Atlas. With telescopes ranging from backyard setups to semi-professional observatories, amateurs worldwide have been contributing position measurements and brightness estimates to the Minor Planet Center. That data is valuable. Professional telescopes can't watch 3I/Atlas every night. There are too many other objects competing for time, but amateurs can fill in the gaps, providing continuous monitoring that helps refine the orbit and track brightness changes. Some of the most dedicated observers have been posting their images online. You can see the faint, fuzzy coma in their photographs. Nothing spectacular, just a dim smudge against the stars. But each image represents hours of work, tracking, stacking multiple exposures, carefully processing the data to tease out the faint signal. It's a reminder that astronomy is still, in many ways, a collaborative effort, not just between institutions, but between professionals and passionate enthusiasts who simply want to contribute to our understanding of the universe. Then there are the space telescopes. Hubble Space. Telescope time is notoriously difficult to secure. The telescope is booked months or even years in advance, and competition for observing slots is fierce. But there's a provision for directors' discretionary time, a small percentage of Hubble's schedule reserved for unexpected, time-sensitive observations. 3I/Atlas qualifies. Dr. Dennis Bodowitz at Auburn University submitted a proposal in early November requesting Hubble time around perihelion. The goal: obtain high-resolution ultraviolet spectra of the coma. UV spectroscopy can detect molecules that are difficult or impossible to observe from the ground, particularly hydroxyl OH radicals produced when water molecules break apart in sunlight. If 3I/Atlas has even a small amount of water ice, we should see strong OH emission in the UV, Bodowitz noted in his proposal. If we don't see it, or if it's much weaker than expected, that tells us something important about the composition. The proposal was approved. Hubble observations are scheduled for December the 20th and 21st, just after perihelion. The James Webb Space Telescope is another possibility, though securing time on JWST is even more challenging than Hubble. JWST's infrared capabilities could detect thermal emission from 3I/Atlas's nucleus, heat radiating from the surface, which would provide direct information about its temperature and size. But as of late November, no JWST time had been allocated. The schedule is packed with high-priority observations of distant galaxies and exoplanet atmospheres. An interstellar comet, however intriguing, has to compete with those targets. Still, there's hope. JWST has provisions for target of opportunity observations. Last-minute schedule changes for unexpected events. If 3I/Atlas does something surprising at perihelion, JWST might be pointed toward it. That's the nature of this kind of science. You plan as much as you can, but you also stay flexible, ready to respond if something unexpected happens. And with 3I/Atlas, the unexpected seems more likely than not. By early December, the object had brightened to around magnitude 16. Still too faint for most amateur telescopes to see visually, but bright enough for serious observers with good equipment. The coma remained asymmetric, faint, and puzzling. Some researchers were optimistic. Maybe perihelion would trigger a dramatic brightening, revealing hidden ice reservoirs and producing a spectacular display. Others were cautious. If 3I/Atlas really is a fragment, they argued, perihelion might not change much. The object might simply absorb the sun's heat without producing significant new activity. The only way to know is to watch. Every telescope pointed toward 3I/Atlas is asking the same question. What are you? And December 19th, whether it delivers drama or quiet confirmation, will bring us closer to an answer. Astronomers are ready. The campaigns are in place. The observations are scheduled. Now it's just a matter of waiting and watching and hoping the weather stays clear. There's a certain comfort in not knowing everything. Science fiction trained us to expect answers, clear revelations, definitive moments when the mystery resolves and understanding clicks into place. But real science rarely works that way. Real science is messier. It's provisional. It's a process of narrowing uncertainty rather than eliminating it completely. And sometimes that's exactly what makes it beautiful. 3I/Atlas isn't going to give us a definitive answer on December 19th. Even with all the telescopes pointed at it, all the spectroscopy and photometry and careful analysis, we'll likely end up with something more ambiguous than a clear yes or no. Maybe the data will lean toward the fragment hypothesis. Maybe it will suggest something else entirely. Maybe it will simply give us better questions to ask next time. That's how astronomy progresses. Not through sudden revelations, but through the slow accumulation of observations, each one refining our understanding just a little more. Consider what we've learned so far. Before August 2024, we didn't know objects like 3I/Atlas existed. We had 2 interstellar visitors in our observational record, and both fit relatively neatly into categories we already understood. The universe seemed orderly, predictable. Then this faint, asymmetric, strangely dense object appeared, and suddenly we had to consider possibilities we'd only discussed theoretically. White dwarf fragments wandering the galaxy, stellar disruptions scattering debris into interstellar space, entire populations of objects we hadn't accounted for. We're not certain any of that is true yet, but the fact that we're seriously considering it, that the data forces us to, is itself a kind of answer. It tells us the universe is more complex than we thought, more violent in its processes, more diverse in its outputs, and that's worth knowing, even if we don't have every detail figured out. Dr. Michael Bannister, reflecting on the 3I/Atlas observations in a recent interview, put it this way: every interstellar object we detect is a gift. It's a sample from somewhere else, another star system, another corner of the galaxy delivered to us purely by chance. We don't get to choose what we receive, but we get to learn from whatever shows up. That perspective matters. It's easy to feel frustrated when data doesn't give clear answers, when objects like 3I/Atlas refuse to fit neatly into our models. But that frustration is itself informative. It means our models are incomplete, and incomplete models can be improved. Think about what happens after December 19th. 3I/Atlas will continue moving outward from the Sun. By January it will be beyond Mars' orbit, fading rapidly as the distance increases. By February only the largest telescopes will be able to track it. Within a few months it will be too faint to observe at all. It will fade from view. But it won't disappear from our understanding. The data collected during these crucial weeks will be analysed for years. Researchers will pore over the spectra, looking for subtle features they might have missed initially. They'll compare 3I/Atlas to other unusual objects, both in our solar system and beyond, searching for patterns. Papers will be published, conferences will debate the interpretations, models will be refined, and eventually a consensus will form. Not because one person proved the right answer, but because the weight of evidence gradually tips the scales toward the most consistent explanation. That's how science builds knowledge. Slowly, collaboratively, with room for disagreement and revision. There's something deeply human about this process. We want certainty. We crave definitive answers. But we've learned, over centuries of scientific inquiry, that nature doesn't always cooperate with our desire for simplicity. Sometimes the answer is, it's complicated. Sometimes the answer is, we need more data. And sometimes, perhaps most importantly, the answer is, we don't know yet. But here's what we're learning. 3I/Atlas has already taught us to ask better questions. Not just, is this a comet? But what range of objects can develop comet-like activity? Not just where did it come from, but how common are fragments from stellar disruptions in interstellar space? Not just, what is it made of, but what does its composition tell us about stellar evolution processes we can't observe directly? These are richer questions, more nuanced, and the answers, when we eventually get them, will be more valuable precisely because they're harder to obtain. That's the paradox of scientific discovery. The easy questions get answered quickly. The hard questions, the ones that push at the boundaries of our understanding, take longer. But they're the ones that actually advance the field. 3I/Atlas is a hard question. There's also something quietly profound about the timing. This object has been travelling through space for hundreds of thousands of years. It passed countless star systems without being noticed. It drifted through regions of space where no planets existed, no observers capable of detecting it. And then, in late 2024, it happened to cross paths with a small rocky planet orbiting an average star in an unremarkable region of the galaxy. A planet that, by pure cosmic coincidence, had recently developed technology capable of detecting faint objects moving against the background stars. The timing is arbitrary. If 3I/Atlas had passed through our solar system 1,000,000 years ago, there would have been no one to see it. If it passes through 1,000,000 years from now, there might not be anyone here either. Or if there is, they'll be so different from us that we wouldn't recognize them. But it passed through now, and we were here to notice. That's not destiny. It's not fate. It's just probability playing out across cosmic timescales. But it still feels meaningful. On December 19th, 3I/Atlas will reach perihelion. It will pass closer to our Sun than it's been to any star in 500,000 years. Solar radiation will heat its surface more intensely than it's been heated in longer than humans have existed. And we'll be watching, with telescopes built by thousands of people over decades, with instruments that can analyze light in ways that would have seemed like magic a century ago, with computers processing data at speeds that would have been incomprehensible to the astronomers who first wondered what stars were made of. We'll watch, we'll measure, we'll record, and 3i/Atlas will continue on its journey, indifferent to our attention, following the trajectory that gravity set for it millions of years ago. It will fade back into darkness, back into the space between stars where most objects spend most of their existence, back into the silence. But this time, it won't be quite as unknown as it was before, because for a few months in late 2024 and early 2025, we saw it. We asked questions about it. We wondered what story it was carrying in its composition and its motion. And even if we don't have every answer, even if some mysteries remain unsolved, we'll know a little more about what's out there, about the echoes that reach us from the void, about the fragments that survive endings and wander through the darkness, about the universe we're part of, even when we can't see all of it clearly. 3i/Atlas is moving away now, but its questions remain, and will be ready when the next visitor arrives.